Now it's time to look at the flexible pavement mechanistic design procedure. Table 8.1, 8.2, and 8.3 list in detail the steps which are required to carry out the mechanistic design procedure. The procedure consists of evaluating the input parameters, then select a trial design and determine the allowable traffic. Finally, compare it with the design traffic and decide to accept or reject the trial pavement. In general, there are 18 steps to follow. Most steps were already covered in previous slides, so I just briefly go through them. You may need to use all of them or some of the steps. The first one is to select a trial pavement and desired project reliability. Then calculate the elastic parameters for the subgrade materials, the E, the mu, and G, followed by the elastic parameters for the top sublayer of the granular layer, and then elastic parameters and thickness of the other granular sublayers. If relevant, we need to determine the elastic parameters for cemented materials and their pre- and post-fatigue cracking. Next, we need to determine the elastic parameters for asphalt, then adopt the subgrade strength criterion for damage type of rotting and shape loss. So afterwards, we need to determine the fatigue criteria, both for cemented materials and asphalt. The 10th step is to calculate the design standard axle repetitions SAR for each relevant distress mode. For the analysis, we assume approximate standard axial view loading, then determine the critical locations in the pavement for the calculations of strength. Step 13 is to input the given conditions to circulate to determine the maximum vertical compressive strength of the subgrade and maximum tensile strength at the bottom of the cemented and asphalt layer. Sometimes we need to calculate the critical strength for both pre-cracking and post-cracking. So if the post-failure cracking phase of cemented materials is considered. For the interpretation of the results, we need to calculate the allowable number of standard axial repetitions for each of the relevant distress mode. For step 15, we compare the allowable number of standard axial repetitions with the design number of standard axial for each distress mode. The pavement is deemed acceptable if all distress modes, the allowable number of standard axial repetitions exceeds the design number of standard axial repetitions. Otherwise, it is deemed unacceptable, then we need to select a new trial pavement and repeat steps 1 to 16. So finally, sometimes we also need to compare the alternative acceptable designs. I will show you one example with 3 types of flexible pavement to help you to understand the above design procedures. This example is the mechanistic design of flexible pavement using the following design parameters. Subgrade design CBR of 5%. Design traffic for 30-year design life is 10 to the power of 7 HVAG. Traffic load distribution is shown in the right table. Operating temperature or effective temperature is WMAPG equal to 28 degrees. Design traffic speed is 60 km per hour. Asphalt modulus for size 14 mm and 20 mm mix. The desired project reliability is given as 97.5%. Let's design the following 3 flexible pavement types. The spread seal surfaced or thin bituminous unbound granular pavement. The asphalt pavement containing a cemented material subbase and full depth asphalt pavement. These are typical flexible pavement types, so let's discuss one after another. Let's look at case 1. The spread seal surface unbound granular pavement. Such pavement is composed of a spread seal layer, an unbound granular layer, and a subgrade. Spread sealing is achieved by spraying a thin film of bituminous binder onto a road surface and then covering it with a layer of aggregate. For the trial design, the first step is try pavement composition with thin top spread seal surface and for 475 millimeter unbound granular material and subgrade design CBR of 1%. The step 2 is to calculate subgrade properties. When CBR equal to 5%, EV equals to 50 megapascal. As EH equals to half EV for unbound materials. So EH equals to 25 megapascal. Mu V equals to mu H equals to 0.45. So shear modulus G could be calculated as EV divided by 1 plus mu V, and we get value of 34.5 megapascal. Step 3, for granular materials placed directly on the subgrade, sublayering is required. The calculation is similar as the example in the last lecture. So EV1 is the minimum of the value from the formula and from the empirical table, which is 500 megapascal. And EH1 again is half EV1, so it is 250 megapascal. The mu V1 equals to mu H1 equals to 0.35 are taken from table 6.3. So shear modulus G1 is calculated as 370.4 megapascal. The ratio R is calculated as EV1 divided by EV subgrade to the power of 0.2, and we get the value of 1.585. Step 4 is the calculation of the elastic parameters for the other granular sublayers. We divide the total granular thickness into 5 equal thick sublayers with 95 millimeter thick for each layer. The elastic parameters for the second granular sublayer from top are EV2 equal to EV1 divided by R equals to 315 megapascal. Correspondingly, EH2 is 157.5 megapascal. So since mu V2 equals to mu H2 equal to 0.35, we could get the shear modulus as 233.3 megapascal. We're able to follow the same procedure to calculate the other sublayers 3, 4, 5. A summary of the calculated material properties are given in the following table. The step 5 and 6 are for cemented materials and asphalt. We don't need to calculate them as they are not relevant to this case. Step 7 is to use the subgrade strain criterion to calculate the permanent deformation allowable loading using this formula, as shown here. And step 8 and 9 are again for cemented material and asphalt, and they are not relevant here as well. Step 10 is to determine the design number of standard actual repetitions SAR for each relevant distress mode. Since NDT, that's 10 to the power of 7 and HVAG, and for this case, the permanent deformation in subgrade is the controlling distress mode. Firstly, we need to calculate the ESA as NDT times ESA over HVAG. And we get the final result of 0.7 times 10 to the power of 7 ESAs. This DESA could be used in the empirical chart in figure 8.4 to determine the thickness of the granular materials, which I will just show you later on. Since SAR7 over ESA equal to 1.6, so that's the given condition of all three cases. So DSAR7 could be calculated as DESA times SAR7 over ESA. So this is 1.6, that's SAR7 over ESA times DESA. And we are able to get the result of DSAR7. So that's 1.1 times 10 to the power of 7 SAR7s. The SAR7 is normally used if designing by mechanistic method. Step 11 is to assume approximate standard actual view loading. The standard actual load is represented as TR pavement contact stress as 750 kilopascal, the load radius of 92.1 millimeter, and 4 circular contact areas. Step 12 is to determine the critical locations to calculate strengths, which are top of subgrade directly beneath one of the loaded views and midway between the loaded views. In previous lecture, we know the locations of critical strengths are the tensile strength at the bottom of the asphalt, the tensile strength at bottom of cemented materials, and compressive strength at the top of subgrade. Since this case contains a spread seal instead of asphalt layer on top, we do not need to consider tensile strength at the bottom of asphalt. It did not contain the cement layer, so we do not consider the tensile strength at the bottom of the cemented materials. So we only consider the compressive strength at the top of subgrade. And one is directly beneath one of the loaded views, and another one is midway between the loaded views. So one is here, and the other one is here. So we only consider the compressive strength. So once you input the given parameters in the circuit, you are able to get the corresponding compressive strength. From the circuit analysis result, it is found that the maximum vertical compressive strength is 906 μ/epsilon, which is midway between the two loaded views. Step 14 is to calculate permanent deformation allowable loading from step 7 in combination with the above maximum compressive strength. The result is 1.2 times 10 to the power of 7 SAR7. Step 15 is to compare the allowable loading with the design traffic. The allowable loading is greater than the design traffic. So we draw the conclusion in step 16 that the trial composition is acceptable. This design was done using mechanistic procedure. For granular pavement within bituminous surfacing, we could use empirical design chart in figure 8.4 to select the thickness of granular materials for trial design. So for flexible pavement with unbound granular material layers, which are surfaced with either a bituminous seal or asphalt layers up to 40 millimeter thick, we could follow the mechanistic design procedure. As it has not adequately accounted the effect of traffic loading on the seam surfacing, we could also use the empirical design chart given in figure 8.4 to determine the thickness of unbound granular materials required over the subgrade. For this empirical design chart, the design traffic loading in the horizontal axis is in ES8. So you calculate the number of load repetitions in equivalent standard actuals over the design period. The other factor is the thickness, depends on is the CBR or California bearing ratio of the materials that is going to be covered by the pavement. So it's shown on the right-hand side axis. Each of these curves here relates to different California bearing ratio. So different strengths of the supporting layers. For this example here, the subgrade has a design CBR of 5, and we had a design traffic loading DSA of 0.7 times 10 to the power of 7. So we are able to find the corresponding thickness of granular materials overlap the subgrade. As 475 millimeter. So that gives the cover requirement over the subgrade to inhibit it deforming and resulting in surface deformation to an acceptable level. So that controls the amount of deformation in the subgrade by providing that amount of cover. The other way is to iterate the DSA and CBR into this formula, and we could work out the same value. This design chart is applicable to pavement with design traffic loading of 10 to the power of 5 to 10 to the power of 8 ESAs.